Okay, let's dive right into this fascinating explainer. Today, we're literally uncovering the hidden architecture of the objects all around us. We are exploring how deliberately combining everyday materials allows us to completely engineer the modern world. We're looking past the surface to decode the hidden science of composites. Think about a skier effortlessly carving through fresh powder snow. It just looks so smooth, right? But beneath their boots, they are actually riding on a highly engineered masterpiece of material science. A modern high-performance ski is definitely not just some plank of wood or a molded piece of plastic. It's an incredibly complex, multi-layered structure that's designed to handle immense stress, completely resist the freezing cold, and glide perfectly all at the same time. So that brings us to a really interesting question. What actually makes a material strong, flexible, and fast all at once? See, when aerospace engineers need a part that's lightweight, incredibly stiff, and highly resistant to corrosion, monolithic materials, like a pure metal alloy or just a standard polymer, usually force a compromise. Basically, if you increase the strength of a pure metal, you almost always decrease its toughness. To overcome those limits, we have to look past monolithic materials and explore the revolutionary world of composites. Here is our roadmap for this explainer. 1. The magic of composites. 2. Anatomy of a composite. 3. The rule of mixtures. 4. Cermets and super tires. And 5. Concrete, the ultimate composite. Section 1. The magic of composites beyond monolithic materials. So the absolute crucial point here is something called the principle of combined action. This principle simply states that by combining chemically dissimilar materials that are separated by a distinct interface, we can unlock super properties that neither material actually possesses on its own. It's literally the ultimate example of the whole being greater than the sum of its parts. We aren't just mixing things together willy-nilly, we are deliberately engineering property trade-offs to get exactly what we want. Now, nature definitely has its own composites, right? Wood is made of cellulose fibers held together by lignin, and our own bones are a mix of soft collagen and hard, brittle apatite minerals. But in the strict context of material science, we're talking about materials that are artificially made. They absolutely must have chemically dissimilar phases separated by a distinct interface. This isn't just a random blend. It's a deliberately designed multi-phase material intended to completely shatter the limitations of conventional metals, ceramics, and polymers. Let's move on to Section 2, Anatomy of a Composite, the two major players. Let's break down the exact internal structure of these materials. Every composite essentially relies on a very specific partnership. First, you have the matrix phase. Think of this as the continuous body that surrounds and binds everything together. Then you have the dispersed phase. This is the embedded material, often particles or long fibers, that provides the targeted reinforcement. So the matrix holds the shape, while the dispersed phase brings the muscle. And there is a brilliant variety of geometric characteristics at our disposal here. The final properties of our composite don't just depend on what materials we use, but on the geometry of that dispersed phase. Engineers have to consider the shape of the particles, their exact size, how evenly they're distributed, and how they're oriented. Altering literally any one of these structural characteristics will directly dictate the ultimate strength and behavior of the entire composite. It's like a giant microscopic puzzle. Section 3. The rule of mixtures. Calculating strength. When we design a new composite, we definitely don't just cross our fingers and hope it's going to be strong. We use a continuum mechanics approach called the rule of mixtures. This mathematical framework lets us confidently predict exactly how stiff or strong our new composite will be, based entirely on the volume fraction of the matrix compared to the dispersed phase. The rule of mixtures gives us two absolutely crucial mathematical boundaries, an upper bound and a lower bound for the modulus of elasticity, which is essentially just the material's stiffness. For instance, if engineers disperse really tough tungsten particles into a softer copper matrix, they know the final material's strength isn't going to be a mystery. By plotting the volume fraction, experimental data shows the stiffness will land precisely between these two mathematical limits. Section 4. Cermets and super tires. Composites in action. So when dealing with particle-reinforced composites, we generally look at two approaches. Dispersion-strengthened composites use incredibly tiny particles. We're talking between 10 and 100 nanometers. They work by actually hindering the motion of dislocations right down at the atomic level, physically restricting plastic deformation. Large particle composites, on the other hand, rely on a much simpler mechanism. The matrix simply transfers the applied stress, basically handing off the heavy lifting to the harder, stiffer embedded particles. And when we talk about large particle composites, the sheer volume of reinforcement can be absolutely massive. In some composites, the volume fraction of those hard dispersed particles often exceeds a staggering 90%. A perfect example of this is a Cermet, a ceramic metal composite, like cemented carbide, which is used extensively for cutting hardened steels. The dispersed phase here is an extremely hard but very brittle ceramic, like tungsten carbide. If you used it all by itself, it would just shatter under pressure. But by embedding those particles in a tough, ductile metal matrix like cobalt or nickel, the metal completely isolates the brittle particles. It literally stops cracks from spreading from one particle to the next, giving us a tool that has the abrasive cutting power of a ceramic combined with the tough resilience of a metal. Conversely, let's look at a composite you probably rely on every single day. The automobile tires on your car contain roughly 15 to 30% volume of a tiny particulate called carbon black. Carbon black is made up of extremely cheap, microscopic, spherical carbon particles, typically just 20 to 50 nanometers in diameter. When they're mixed into vulcanized rubber, they form a remarkably strong adhesive bond with the rubber matrix. Without this specific interaction, modern synthetic rubber tires would totally lack tear and abrasion resistance, and honestly, they would literally disintegrate rapidly out there on the road. Section 5. Concrete, the ultimate composite. I'm talking, of course, about Portland cement concrete. The recipe for this stuff is a masterclass in composite design. You have the Portland cement acting as your matrix, then you add your dispersed phase, a combination of coarse aggregate, which is basically gravel, and a fine aggregate, which is sand. Add some water to initiate the chemical bonding, and you're all set. The mixture is carefully balanced so the fine sand perfectly fills the microscopic gaps between the gravel, and the whole shebang is thoroughly coated by the cement water paste. What's really amazing here is the sheer economics of this material. The aggregates basically act as a filler, typically between 60 to 80%, so let's just say an average of 70%, of a block of concrete is just cheap filler rock and sand. The more expensive cement only makes up about 30% of the volume. This is exactly what makes it such an incredibly economical building material that can just be poured right at room temperature. However, concrete has a massive structural flaw. Like most ceramics, it is extremely brittle. While it can withstand unbelievable crushing weight, which is its compressive strength, its tensile strength, or its ability to be pulled apart, is frankly terrible. It's only 1/15 to 1/10 of its compressive strength. Add to that its vulnerability to water penetrating its pores and expanding during freeze-thaw cycles, and, well, concrete alone simply cannot build a skyscraper. It desperately needs a composite partner of its own. And that is exactly why we created reinforced concrete. By embedding steel rods, or rebar, right into the uncured concrete, we completely overcome that ceramic brittleness. The steel easily handles all those pulling, tensile, and shear stresses. And brilliantly, steel is used because it shares nearly the exact same coefficient of thermal expansion as the concrete. This means they expand and contract together in the weather without ever breaking their adhesive bond. By adding rebar, or using pre-stressed techniques, we create the ultimate structural foundation. From the high-performance core of a snow ski to the towering concrete and steel skylines of our greatest cities, the principle of combined action fundamentally shapes our physical reality. I really hope this explainer has completely changed how you look at the mundane objects around you. Because once you actually understand composites, you have to wonder, as we look down to the nanometer scale and beyond, what incredible, revolutionary supermaterials are just waiting to be mixed next?